In the realm of classical physics, objects move in predictable paths. We throw a ball and it follows a parabolic trajectory. A planet orbits a star in an ellipse. These paths seem predetermined, governed by forces and Newton's laws of motion. However, quantum mechanics, the physics of the very small, challenges this view. It proposes a radical idea. Particles don't follow just one path, but explore all possible paths simultaneously. This concept, known as path integral formulation, is central to understanding the strange and counterintuitive world of quantum phenomena. Imagine a car at a crossroads. Classical physics tells us it will take one specific route. Quantum mechanics, however, suggests the car travels all routes concurrently, like a phantom car splitting and merging along every possible path. This may seem absurd, but this concept helps explain some of the most fundamental mysteries of the universe, from the behavior of subatomic particles to the nature of light and matter. The concept of path integrals is closely tied to the principle of least action. This principle, a cornerstone of physics, states that nature always chooses the path that minimizes a quantity called action. Action, roughly speaking, is a measure of the energy expended by a system over time. Think of it as the effort required for a particular motion. A ball thrown upwards will follow a parabolic path, the path of least action, as it balances kinetic and potential energy. Pierre-Louis Maupertuis, an 18th century French scientist, first introduced the idea of action. Later, Irish mathematician William Rowan Hamilton refined it, developing a mathematical framework that underpins much of modern physics. The principle of least action is not just an abstract mathematical concept. It has profound implications for our understanding of how the universe works, from the motion of planets to the behavior of light. The development of path integral formulation and the understanding of its connection to the principle of least action involved a cast of brilliant minds spanning centuries. As mentioned, Maupertuis and Hamilton laid the groundwork with their work on action. Max Planck, with his revolutionary idea of quantized energy, ushered in the era of quantum mechanics, setting the stage for a radical shift in our understanding of physics. Albert Einstein, building on Planck's work, explained the photoelectric effect by proposing that light, too, comes in discrete packets of energy called photons. Niels Bohr applied quantum ideas to the atom, explaining the stability of electron orbits. Louis de Broglie further blurred the line between waves and particles, suggesting that matter, like light, exhibits wave-like properties. This wave-particle duality is a key concept in quantum mechanics. Finally, Richard Feynman, an American physicist known for his playful approach to complex ideas, developed the path integral formulation of quantum mechanics. He showed that instead of calculating the trajectory of a particle, we should consider all possible paths and their associated probabilities. The double-slit experiment, a cornerstone of quantum mechanics, beautifully illustrates the wave-like behavior of particles. In this experiment, particles are fired at a barrier with two slits. Instead of behaving like tiny bullets that go through one slit or the other, they create an interference pattern on a screen behind the barrier. This pattern is characteristic of waves interfering with each other. When waves overlap, they can either reinforce each other, constructive interference, or cancel each other out, destructive interference. The bright and dark bands in the double-slit experiment are a direct result of this wave interference, but here's the kicker. This interference pattern appears even when particles are sent through the slits one at a time. This implies that the particle, in a sense, goes through both slits simultaneously, interfering with itself. This is a profound departure from classical physics, where a particle can only occupy one position at a time. Section 5. Diffraction grating, the interference of light. Diffraction gratings provide another striking example of wave interference. These are surfaces with closely spaced parallel lines that act like multiple slits. When light passes through a diffraction grating, it gets diffracted, meaning it spreads out. This spreading out leads to interference patterns similar to those seen in the double-slit experiment. The spacing of the lines on the grating determines the angles at which constructive interference occurs, resulting in bright spots at specific locations. Diffraction gratings are not just laboratory curiosities, they have numerous applications in science and technology. They are used in spectroscopy to analyze the composition of light, in telescopes to separate light from distant stars, and in CD and DVD players to read data. Section 6. Action and amplitude quantifying quantum paths. In Feynman's path integral formulation, each path a particle can take has an associated amplitude. This amplitude is a complex number that encodes information about the probability of observing the particle following that particular path. The amplitude of a path is related to the action of that path. Paths with lower action have higher amplitudes, meaning they are more likely. This is where the principle of least action comes into play in the quantum world. The paths with the highest amplitudes, and therefore the highest probabilities, are those that are close to the classical path of least action. Calculating the amplitude for a given path involves complex numbers and mathematical tools beyond the scope of this essay. However, the key takeaway is that the amplitude for a path is determined by the action of that path, and paths with lower action are more likely. Section 7. The quantum classical divide, why we see what we see. If objects explore all possible paths, why do we observe them following a single well-defined trajectory in our everyday experience? The answer lies in the nature of quantum interference and the vast number of possible paths involved. For macroscopic objects, the action associated with each path is very large compared to the reduced Planck constant, a fundamental constant in quantum mechanics. This results in extremely rapid oscillations in the amplitudes of different paths. When we sum up the amplitudes of all possible paths, these oscillations mostly cancel each other out due to destructive interference. The only paths that contribute significantly to the final probability are those very close to the classical path of least action. Therefore, macroscopic objects appear to follow classical trajectories because the vast majority of quantum paths interfere destructively, leaving only the classical path as the most probable outcome. Section 8. Implications and applications from lasers to quantum computers. The concepts of path integrals and the principle of least action are not just theoretical curiosities. They have led to profound technological advancements and continue to drive innovation in various fields. Lasers, for example, rely on the principle of constructive interference to produce highly focused beams of light. By carefully controlling the paths of light waves, we can amplify their amplitudes, resulting in the intense, coherent beams that power everything from barcode scanners to laser surgery. Quantum computers, another groundbreaking technology, exploit the principles of quantum mechanics, including superposition and entanglement, to perform computations that are impossible for classical computers. Path integral formulation plays a crucial role in understanding and designing these futuristic machines. Section 9. Conclusion: embracing the quantum perspective. The path integral formulation of quantum mechanics offers a radical departure from our classical intuition about how objects move. It tells us that instead of following a single predetermined path, particles explore all possible paths simultaneously, with the observed path emerging from the complex interplay of quantum amplitudes and interference. This view, though counterintuitive, has proven incredibly successful in explaining a wide range of phenomena, from the behavior of subatomic particles to the nature of light and matter. It has also paved the way for technological marvels like lasers and quantum computers. As we delve deeper into the quantum realm, we continue to uncover new and surprising aspects of reality, challenging our understanding of the universe and opening up new frontiers in science and technology. The journey through quantum paths is an ongoing adventure, full of wonder, mystery, and the promise of groundbreaking discoveries.